Okay.
I messed up again. All right, you're good.
Okay, sounds good. Hi, everyone. My name is Arya Joshi. I'm the consult team lead for CPV Hyperloop, and I'm also a third-year mechanical engineering student at Cal Poly Pomona. So today we're going to be briefly talking about CAD, but we're going to be talking about how we can convert files from something like Fusion 360 to SolidWorks, because what you'll notice is throughout the semester when you're working with design team and maybe even outside of a Hyperloop, you might be using different types of softwares to do your design work. And sometimes maybe it's better to use one software over the other. Like for instance, Fusion 360 is easier to use. So some would say, and SolidWorks has much more tools that you can use to conduct analysis of your design. So we're going to be talking about how you can convert your files using step files to kind of operate between two different softwares. And then we're going to be going over how to make drawings on SolidWorks. And I think a lot of you who have experience with SolidWorks know how to make drawings, but we're also going to be going over GD&T, which is the geometric dimensioning and tolerancing, and perhaps maybe you might not be familiar with that. So yeah, let's start. And before we start, I'm just going to go over what CAD is. I like to do this before each of the workshops, just in case there are new members who are kind of like getting familiar with CAD. So CAD basically just stands for computer aided design. And you can see like the images, like people in the past used to like hand draw stuff to kind of express what type of design they wanted. So, you know, if you look back, you know, you'll see a lot of intricate drawings with dimensions and all that stuff to kind of show, you know, that this is what we want to build. But nowadays, you know, we use computers and we can basically design stuff using SolidWorks and other CAD modeling software. So basically, there are free CAD softwares provided by Cal Poly Pomona, no cost to you. And, you know, you should make use of these tools, especially right now, because since they're free. When you go into industry and when you leave college, a lot of these programs are going to cost a lot of money. Like SolidWorks, I think costs like a couple $100 per year just to use. So, you know, if you download these softwares, you'll get more experience with them. And also they're good tools that you can put on your resume if you're skilled enough, because a lot of companies and internships look for some experience with these types of softwares. So I've put a link here below, and it's basically on the CPP website, and you can check it out. So yeah, I'll leave that there, and I can put that into the Discord chat later. Okay. So what I'm going to do now is I'm going to transition towards Fusion 360, and then we'll get started with step files. So I'm going to stop share this, and then I'm going to go over to Fusion 360. Okay. Could you see my screen? Yes. Okay. All right. So now this is a design that we were thinking of for our I-beam. And I believe this is a design from last summer. So basically, like this is a Fusion 360 CAD design, right? And let's say we want to make a drawing of this using SolidWorks. So how would we do that? So if you go under File, and if you press Save As, like we would with any other normal file, you will see that it doesn't give you an option to save it onto your computer. Okay, so it just gives you a location on Fusion 360. So what you want to do is actually you want to go to export, right? And you can name it whatever you want. I'm going to name it beam. Okay. And you want to choose step files. So step files are basically a type of design file that you can use for different platforms. So Solidworks would not be able to open a Fusion 360 file, or a Solidworks file wouldn't be able to be open on Fusion 360, but you will be able to open step files on any of those softwares. So we're going to choose step files and press export. Okay, so it says export is ready. So now you can just basically put this onto your computer. So I have it under downloads. And now I'm going to open up SolidWorks. Could you see SolidWorks, or do I have to share my screen again?
Share screen.
Okay. Okay. So you should be able to see it now. We're going to go to File. We're going to open. Let's see, downloads. Actually, yeah, it's taking a while, but sometimes it does that. Sometimes it's automatic, but it should work. So yeah. So this is basically the I-beam that we saw in Fusion 360. Give it a moment to load completely. Right, so this is basically the Fusion 360 design in SolidWorks, right? So that was pretty easy, that was pretty basic. And what we're gonna do now is we're gonna start making a drawing. But actually, before we do that, I wanna go over GD&T. So when we're making the drawing and we incorporate GD&T into our drawings, we'll have a better understanding of what those values are. So I'll stop my screen sharing and I'll go back to the presentation. And I'll talk a little bit about GD&T. Okay, so GD&T basically stands for geometric dimensioning and tolerancing. And it's actually a slang term. I know a lot of industry professionals use it, but it's actually a slang term for ASME Y14.5 dimensioning and tolerancing standard. So that's the code that ASME has set to kind of deal with tolerances and dimensionings with designs. So on your right, you can see an example of what GD&T would look like. So there would be like a geometric characteristic, shape of tolerance zone, and all these other types, other values. So we'll get more into that later. But basically, the traditional tolerancing method is that you leave a room for tolerance, right? So, there is there's an allowable amount of variation that you're willing to accept in your dimensioning. So if you're making something, I don't know, like a vehicle part for subassembly, maybe you want it to be 5 inches, but you're willing to have a little bit of deviation in that dimension by 0.01. Okay. And that's something common that happens in manufacturing just because they can't get it to the fine exact, 5 inches, right? There's going to be some room of error. And, the thing about tolerancing is that you want to kind of basically keep in mind that you want to have, an around exact number, like you want to be precise with your dimensions, but also precision comes at a cost, right? So If you're wanting to be a lot precise, then the cost is going to go way up because they would have to use new types of technology, more expensive types of technology to kind of make it fine-tuned. So basically what we use GD&T for is to really understand tolerances, and how they're different from traditional tolerancing methods is that it comprises of this thing called the geometric characteristic, and there's also other features that make it more suitable for people who are trying to use the part that they're designing for a greater subassembly, right? So I want to give you an example of an O-ring for a rocket ship, as you can see on the left corner. If someone gave you an O-ring, right, just like that, you wouldn't know what to do with it. And you would, if someone told you, hey, give me a schematic on how you're going to design a rocket booster, you wouldn't know what to do with it because you don't know how to assemble it. However, when you start getting a better understanding of how this is exactly going to be attached into what parts, you can start making the actual model, right? So basically, O-rings are kind of are actually used in rockets for containing the rocket boosters, and you really want to figure out, okay, what's the smoothness of the O-ring going to be like? What's the tolerance for the O-ring? And so all those components are required in order to actually create a functioning, prototype or model. So that's what GD&T is for. And this is actually a very useful slide because today we're going to be talking about geometric characteristics. And that's basically what we're going to kind of focus on today, because GD&T, I mean, you can spend an entire week to kind of really understand what GD&T and how to use it when you're doing your own drawings. But basically today we're going to talk about the basics of GD&T, and which is the first thing, right? If you go back, you can see that the first thing is the geometric characteristic. So that's what we're going to be talking about. So basically the geometric characteristics are a bunch of these like small like these symbols, right? And they all mean something. So the first, like the circle with the center across is position. This one is flatness, right? There's concentricity, symmetry, straightness, right? So basically those are characteristics of the design itself. So for instance, let's say you want to have a flat surface, right? Maybe you need a flat surface for whatever project you're doing or for whatever assembly you're going to be making, right? So you want to, create, a GD&T that defines the tolerance that you're going to have for the flatness, right? So if you look at the example on the top, it talks about flatness. The first is dimensioning or tolerancing, right? So it's going to be between maybe 2 inches and 1.5 inches, right? So there's going to be a maximum of 2, minimum of 1.5. So there's deviation there. And for the GD&T, what we have is we're looking at tolerance of the surface, right? So we want the surface to be flat, and we're willing to accept a tolerance of 0.16. So you can see that on the left, on the left, and you can see that on the right, where the deviation between the top curve and the bottom curve is around 0.16. So that kind of informs the manufacturer or whoever's making this that, they're willing to accept this much deviation in the smoothness of the top. Also, you can see another example on the bottom where we're looking at the straightness of this cylindrical rod, right? Maybe you're using this for a shaft, maybe you're using this for a bearing, and you want this to be pretty straight. So you're willing to accept a tolerance of maybe 0.003, right? And you use the flat line to indicate this stands for straightness, right? So it's the same thing for everything else, like angularity is the deviation in angles. Perpendicularity would be the deviation from a perpendicular kind of perpendicular standpoint. Parallel, you know, whether two objects are parallel to each other and whether there could be deviation there. Concentricity, you know, how far from the center. So basically all of these mean something, and use them appropriately when you're making your drawing. So now we're going to start making our drawing. I'm going to stop my screen sharing and transition back to the SolidWorks, and then we can go from there. Okay. So we're first going to go to File. We're going to go to Make Drawing from Assembly. Okay, and first I'll have to save file. To save the file again. Because see, this is pretty interesting, right? Because we first saved it as a step file, and now we're going to be saving this as a SolidWorks assembly file, right? And this is not a part, even though it is just one object. It's not a part. It's an assembly because we actually use step file, and when you open a step file on SolidWorks, it automatically classifies it as an assembly. So go to downloads, and I'll call it beam again. I'll save it. Okay, so now we can make a drawing. Okay, so basically when you open up the drawing tool, you'll get a bunch of these options, and this is just basically formatting, and you can change this whenever you want. But basically, you can use this to kind of get an idea of how big or small your drawings are going to be. So it's going to scale it accordingly. So I'm going to choose B just for sake of example. Okay, and you can see on your right there are certain pictures, and these are pictures of the IB, and we're going to be using these to create the drawing. So all you have to do is kind of drag it to the paper. So for instance, the front, drag it here, right? Now you can see that's pretty small, right? And you want to make it big so it's like easier to read. Okay. Yeah, so it's kind of hard to read. So what you want to do is you want to go to Sheet, and then you want to go to Properties, right? And you want to look at the scale, right? So basically, the scale is 1 to 5. Maybe make it like 1 to 3. See, it gets bigger, right? Actually, let's do 1 to 2. Maybe we can make it a little bit bigger. Okay, yeah, so that's an appropriate size to kind of do an analysis on this. When you're making a drawing, you want to have 4 drawings, right, or 4 kind of perspectives of your model. So if you go back to the palette, you can see like this shows the top, right? If you were looking from the top onto the I-beam, you would see something like this. But you also want to get an understanding of how it would look from the front. So, you know, you can put something like this, right? Now, this gives a better understanding of how the front looks like, right? And then you also want to add the left or the right. Doesn't really matter, but just move this. Right, so now you have a better understanding of how it kind of looks like. So on the top, it's basically a flat surface with these little, kind of like these little pins sticking out, rectangular pins sticking out. The kind of the front looks like this, like normal I-beam, and the left side looks kind of like this, So, and then at the top right, you want to add an isometric view. So basically this kind of shows what it's actually going to be looking like. It's actually going to look like. So it's hard. It's kind of like sometimes it gets hard to kind of position these because they create relationships with some other the other drawings, and then it's hard to move it by itself. But yeah, so okay. Yeah. So here, if you go to display style on the bottom, you can kind of, right now it's kind of like drawn out, but you can kind of fill in the colors, so it looks more professional. But see, so that's basically what we're trying to create. These are the sketches of the y-axis, x-axis, z-axis, right? For those different perspectives. Now, if you go to smart dimensions, you would be able to draw, or you would be able to kind of call out the dimensions. Okay, I believe these are in inches, right? So, right, so this would be 5 inches, right? Or the length of it, or I guess the width of it would be 5 inches. If you look at here, the length would be 8 inches, right? And then you can also do the radius of curvature, right? That's going to be 0.5. I believe that's going to be in radians. And yeah, so you kind of get the gist of, you're basically using smart dimensions and you're clicking on the lines and shapes where you want to kind of note what the actual value or the dimension is going to be. And, these are kind of like, you don't have to do anything. You don't have to type it in. When you are making this drawing, you entered those dimensions in. So when you make the drawings, you'll just use those dimensions. So, it's pretty neat because we made this design on Fusion 360 and we did all the dimensions on Fusion 360. And now we were able to, use this on Solidworks and make a drawing with the same dimensions and everything saved. So it's pretty cool. Now I'm going to show you how to do manual tolerances. So like, for instance, let's say you want to make the length have a tolerance of maybe 0.01. If you go under tolerance and precision, right now it's selected as none. That's why there's nothing there. But if you choose something like, let's say, symmetric, right? Symmetric basically means that tolerance, maximum tolerance and the minimum tolerance deviate by the same amount. So like in this case, if it would be something like 0.01, then you can see like it's the minimum would be 4.99 and the maximum would be 5.01, right? Or you don't have to do symmetric. You can do something else. You can give a certain minimum value and give a certain maximum value. But for the sake of example, we'll just use symmetric tolerance. And, we can do the same thing for each of the other, dimensions. Now, I want to go to view layout. Sometimes what happens is that your drawings or your models are so intricate, and there's so many small details, it's kind of hard to see on drawings, right? Like this design is pretty simple, but like, for instance, if I was going to annotate these little holes, it's kind of hard to do so because like they're pretty small and it's hard to read. So what we can do instead of doing this is we can go to view layout and we can do a detail view. And I can select this. Okay. So now this gives me a better picture of what's going on. And like I said before, like we don't really need to do that in this case, just because you know, it's pretty easy to see already. But you know, it kind of gives you a better understanding of the small details. And then there's also a section view that we can use. Okay. Basically what the section view did in this case is it kind of like sliced the I-beam in half at the midpoint, and it kind of gives you the image of that slice, right? So the reasons why you would want to do something like this is sometimes you don't see certain types of geometries. So for instance, here you just see like you know, on the back you don't see any holes. Like, you know, when we're actually joining the I-beams together, you know, we have pins on the front and then we have holes in the back. So when we make a lot of these, we can just, you know, stick the pins into the holes and it creates a uniform I-beam. So, but here in the design on the top left, you know, you don't see those holes on the back, but here you can see them, right? So that's why like doing a section view might be important in some cases, you know, and then you know, you can give dimensions to those as well, right? So this basically paints a holistic picture of your designs. So it's much easier for the manufacturer to know, you know, exactly what you want, because there are a lot of times where, you know, you have a design, you have an idea of something, and then you send it out to get it manufactured, and then you get something completely different because, you know, they didn't really understand what you were trying to design, what you were trying to make. So this is how you would do something like this. And then now we're going to go to geometric tolerance. That's what we were talking about before. When you go to geometric tolerance, you'll see kind of the same setup as we did in the slides, right? So we start off with a symbol, then we have tolerance, then we have something called tolerance 2, then it's primary, secondary, tertiary frames. You know, we're not going to get into that right now. That's a little bit complicated, but we're gonna talk about the symbol and tolerance. So let's look at what we want to kind of do a tolerance for. Let's say you want to do a tolerance for the top surface because, you know, you want to keep the top surface smooth so there isn't any problem with the Hyperloop pod to actually travel across the I-beam, right? If there's a lot of bumps or if there's any types of extrusions on the top, it might kind of impede the motion of the Hyperloop pod. So maybe we can do a flatness tolerance for the top. So you go to geometric tolerance, you choose a symbol, you use a line, which, you know, indicates tolerance for flatness, and we can give a tolerance of 0.01. Let's just say, you know, it can be 0.001, but just for the sake of example, again, we will just use 0.01. There you go. Oops. Actually, right. So now basically that indicates that there's a tolerance of 0.01 at that point, right? And, you know, we can do the same thing for something else. Maybe we want, actually, let's see what other options they have. Yeah, maybe you want something to be parallel. Actually, let's do perpendicular. So for instance, here we want this to be perpendicular for some, like, and we have a certain tolerance called for this. And if it kind of is greater than the tolerance that we allot for, maybe the track won't work or something like that. So what we can do is we can click on this and we can go geometric tolerance and perpendicular symbol. You can give it a tolerance of 0.01. So that just indicates that that's the tolerance for the actual perpendicularity of the I-beam, at least for that portion. So that's pretty much it for GD&T. There are some other tools that you can use on drawings to make your drawings more specific. You can use datums to call out stuff. So for instance, I can use datums, and usually datums are used. We're not going to go over it too much detail, but datums are used to indicate points of contact between this part and another part. So like I said, GD&T are very useful for subassemblies. So the datums kind of basically indicate where the parts are going to mate. So like if a part is going to be attached to another part, exactly what surfaces is it going to be attached to, and that's what the datum would kind of indicate. So we can use those to indicate those points. We can make notes, write stuff down. This is front. And if let them know that this is the front side or something like that. Or if you have anything like you want to add to the drawings, or you want to kind of clarify to the manufacturer, you can do that. And for proper formatting of the drawing, you want to fill in these blanks. And I'll show you how to do that right now. So you go to sheet format and you go to edit sheet format. Now you'll be able to edit these boxes. Right here, ideally you want to put like I don't know, like just like your design, your part number or something related to your design. So maybe I can say beam, version, V1 or something. Basically, that kind of indicates that this is the I-beam. Actually, let's make it I-beam. But this is the I-beam. This is our version 1. Maybe that means that this is a rough draft or something. Right. And drawing number, usually this is for like if you have a portfolio of drawings. So if you're making a bigger assembly and there's a bunch of parts, then you would give it a drawing number, maybe like 1, assembly 1, part 1, something like that. You can give it a title. You can use that to put like the company name or whatever. And then here, these are pretty important, and I guess really depends on how strict your company or you are with these kind of options. So there's who drew it, there's name and date, who checked it. Usually this is used in industry, right? Before we manufacture anything, we want someone to check it just to make sure there aren't any mistakes, whether it's safe to use. So there's someone who checks it. And then there's any comments. Again, this is another place where you can make any comments to the manufacturer, the machine shop, to kind of basically, kind of keep in mind when they're making your part. So that's pretty much it. There's material, you can specify what the material is, because even if you specify your material on Solidworks, it's not going to show up here. So you can specify your materials here. That's pretty much it for GD&T and making a basic drawing. I know this kind of looks a little bit messy because things are a bit large, but you can, again, like I said, you can always format them to make them smaller, to make them fit your needs, be able to fit everything in. If you have a lot of small details, then you have to make room for that, so you can basically make your drawings a little bit smaller. That's pretty much it for drawings and tolerances. Does anyone have any questions about any of this?
Arya, could you quickly talk about how, if you have like multiple dimensions, let's say if you're if you want to find the dimension of that, maybe like the left bottom part of the I-beam and then like the flange of the I-beam, which is like the small middle part, how would you dimension multiple things to the manufacturer?
Mention multiple things that I'm kind of confused with your question. So like, are you asking like what the dimensions would be for these parts?
I'm probably more or less asking like if you have multiple dimensions on like one side or like the bottom side or like the top side, I guess how would you do that for the manufacturer? Because like they don't know the dimension, or yeah, let me try to phrase this better. How would you like fully dimension at least the front view as of right now?
Oh, I see. Okay. So I can go over like if we're gonna basically make the entire front, how we might be able to do that. So for the first thing is that you want to make sure that you have all of these defined, all the lanes defined, right? And let's see, let's keep on going and let's actually fully define the front. Okay, sometimes you want to steer clear from certain redundancies. There are certain types of dimensions which you can kind of define on the top and also on the bottom, but they're kind of redundant to do so. So maybe you don't want to kind of like overcrowd your drawings, but like for instance here in this case, you don't really need a 3.68 here and a 3.68 here because it's kind of the same thing, right? You can get rid of that. But you can look at these. This is 0.05, right? And I think Chris, you were asking about like how we can do tolerancing for these dimensions. Is that what you're asking?
Right, and like where would you position them in the diagram? Because I think it'd be really confusing if they were all over the place.
Yeah, I see what you're saying. Yeah, so if you were gonna, let's do a GD&T for this, like similar to what we did here. So let's say you want the bottom to be smooth too, because you don't want it to kind of be a rough surface. Maybe if you're going to put onto like a flat round area, and maybe that might kind of impact the stability of the I-beams, then we can do a geometric tolerance for this as well for flatness. 0.01. Oh, I forget, but you have to click on the length first before you do that, so it knows to kind of designate it to that area. Okay, yeah, so basically, this is what you want to do. And here, maybe we can have a tolerance, 0.01 like the other one. Right, so what we have is, kind of want to adjust everything so it looks clearer. Right, the length of the bottom part of the I-beam is 4.88 inches with a tolerance of 0.01 inch. The tolerance of the smoothness of the top is 0.01 inch. Right. We can kind of adjust this. Yeah, that's pretty much it. You can make tolerance for this too. And also, I forgot to mention this when I was doing tolerance for the first time, but when you go here, you can kind of like choose digits you want. So if you want more precision, then maybe you can choose, up to the thousandths or 10,000ths, But in this case, the hundredths is pretty okay for us, but the options there. But yeah, so that's pretty much it. I mean, if you're gonna have different, you're gonna have different profiles, different dimensions for the lengths, the widths, the flange. So you just want to indicate exactly for that specific length or width, or whatever it is, and what the tolerance is going to be. And that's pretty much it. You want to be pretty specific with your drawings. You don't want to leave anything out. Here we've kind of like, for instance, we can do another smart dimension and indicate that this is 90 degrees, it's perpendicular. But we don't really need to do that because we already indicated perpendicularity here with the tolerance. But yeah, that's pretty much all there is to it. Yeah. Anything else?
For me. You guys have any questions? All right, awesome. All right, Arya, I think we're good.
Okay. Yeah, I mean, yeah, if no one has any questions, then I can end it. Yeah, so it's pretty straightforward. You kind of export, regardless of what software you're using, kind of export your files using the step file function or that type of file, and then you can open that on SolidWorks or Fusion 360. I'm pretty sure you can open on AutoCAD as well. And then basically after that, you can do whatever you need to do on the other software. Drawings are pretty easy. You just kind of use a smart dimension tool to make the dimensions, and they give you options on doing tolerances on the top, and also when you're making those smart dimensions, or when you're calling out the specific lengths and the widths and the heights and everything, they give you an option to include tolerances. It's pretty simple. And if you don't have any questions, then yep, that's pretty much it.
All right. Thank you, Arya.
Thank you.
All right. See you, everyone.